Hi, everyone. Thanks for coming. All right, so let's get started. So this talk is intended for everyone. So whether you've used Chef Vault before or you're looking to make it work for a large-scale infrastructure, say thousands, tens of thousands of nodes, or just getting started into securing your secrets in your infrastructure. So basically, I'd like to share with you guys the issues that we've faced and how we've solved them. So briefly, we're just going to go through an overview. So we're going to go through the problem, possible solutions, proposed solution, next steps, and we can do a quick Q&A after. So what is the problem? So as your team grows, there should be a more secure way to store your secrets. These could be app credentials, certificates, whatever sensitive data that you might have. In your team, there should be different access controls for different people or different groups of people. And there should be different credentials for different environments, nodes, data centers, or any other logical grouping that you might have. Another pretty obvious problem is that secrets shouldn't be hard-coded. They shouldn't be in plain text and just push to whatever source control that you have. And there should be an easy way to update or rotate credentials across your infrastructure. And lastly, there should be a more proactive mindset rather than reactive when it comes to your infrastructure security. If you've failed to plan, you've planned to fail, as they say. You shouldn't wait until it's too late. So about this time last year, around July, there was a problem with the New York's MTA. So basically, the vending machine stopped working. So you just imagine having long lines of people pissed in the subway. There's this guy named Miguel who had the password for their systems. And they couldn't bring back the systems because they didn't have this password. They couldn't reach this guy who lives hours away from New York because he turns off his cell phone on the way home. So storing your passwords with a guy like Miguel is definitely not ideal. And there should be a better way of handling something like this. So what are the possible solutions? Of course, you can store your credentials in plain text. You can put it in your node attributes, Chef encrypted data bags, HashiCorp Vault, which is pretty popular. Square Schibas, and there are other solutions out there, but we're not going to go through those. We're going to go through the 5 that is on the list. So, of course, low-hanging fruit. This is the easiest way to propagate your configuration, right? So you can just type in your username, your password in plain text, and push it everywhere you want it to be. But the problem is it's in plain text and not secure at all. If you want to get a little bit more fancy, you can put your credentials in node attributes, but much like plain text, still not secure. And you'd have to get into the node attributes to debug stuff. Another way would be to store your credentials or secrets in encrypted data bags. It is open source. It is built into Chef. And you'd be able to encrypt data containing sensitive information. But the problem is there's a shared key there's only a shared key to decrypt the data bag, and you have to handle the sharing of the key. Another popular option is HashiCorp's Vault. It's one of the popular options that you might be able to use to secure your credentials. It is not tied to one configuration management system. It is API-based. There's LDAP support. But the problem is there's added complexity to what Chef and Chef Vault can already offer. Another good option is Square Schibas. So much like the others, it is open source. Can be customized with LDAP as well, API-based. But the problem is groups are not hierarchical, and cannot be in other groups. Secrets are stored in memory and never persisted to disk. So if the file system is unmounted or the server loses power, all the secrets will be gone from your server. So a brief overview of the options that we have, minus the chef node attributes and plain text. So you'd have encryption for all of them, managed distributions only available for HashiCorp Vault, Square's Keybase. You have grouping for all of them. There's chef integration for encrypted data bags and HashiCorp Vault, audit trails for HashiCorp Vault and Square's Keybase. But what we're trying to optimize is the overhead. So what is our proposed solution? Here's Chef Vault. So it is also open source. Much like encrypted data bags, it has the data encryption that you would need, but you won't have the constraint of having one shared key across multiple users and or devices. And it has granular control over your secrets up to the user level. Multiple clients can be grouped via roles. But the problem is this is only specific to Chef. There's no readily available API compared to HashiCorp's Vault or Square's Keybase. And you need to know the list of nodes at encryption time. Every time we want to add or remove nodes, we have to re-encrypt the whole data bag. So a little bit of history. So Chef Vault was originally developed by Nordstrom. In 2015, it got transferred to Chef. So thanks to Nordstrom for a wonderful project. So how does it work? So as I said, Chef Vault is built on top of Chef encrypted data bags. In encrypted data bags, you basically can have a user and a node decrypt the same data bag, but you'd have a shared key between them. And that is one of the problems that we're trying to solve with Chef Vault. So how does Chef Vault work? So imagine you have a Chef server and 2 nodes. Each node is represented by a node client object in your Chef server. And each node can be managed through an RSA key pair. So public keys would be stored in the Chef server. Your private keys are in the nodes. There we go. And essentially, we can use this key pair to encrypt our sensitive information in our Chef Vault. So basically, what's happening is there's a 2-layer protection. So using the public keys for your users or your nodes, it basically encrypts a shared secret. And that shared secret is also used to encrypt your actual data in the vault. So twofold protection. So you have encryption via RSA key and also an encryption via shared secret. So let's get to the specifics of what issues we've faced at AppLovin and how we've solved them. So let's go to the next slide. So in a large-scale distributed system, so you can have thousands, tens of thousands of nodes, you can basically have an elastic infrastructure with a constantly changing number of nodes. So you can have hundreds of nodes being deleted, hundreds of nodes being created probably 5 minutes after. And it also depends on the demands of your business, basically. These nodes have credentials that are stored and accessed via Chef Vault. Let's see. Next slide. So one of the big issues that we've faced at AppLovin is that some of the resources in Chef Vault are actually causing some deadlock, especially when you try to run multiple jobs or multiple Chef Vault operations all at once. So for example, you have node 1 trying to access a resource, but it's actually being held by another node. So we've solved that by actually putting proper locks into the resources and implementing thread pools within Chef Vault. So imagine you have multiple nodes trying to access a resource. They would be accessing locks and put into a thread pool. And as they complete their operations, they would then be put into a completed list. All right. So another thing that we found helpful in addition to thread pools is using sparse mode. So this is the typical way of how you create a vault item. So you do a knife vault create, your vault, and then the item name, and you can pass in -k sparse. Unfortunately, there is not much documentation on this, but sparse mode essentially shards your Chef Vault resources for a particular vault item, and it helps in doing operations like refresh or update more efficiently. So in the Chef server, what's happening is you'd have separate files for public keys of each user and each node. And okay. All right. So another issue that we face with Chef Vault is the actual bootstrapping procedure. So we use roles to determine a logical grouping of nodes. So you can have an old node being deleted and a new node being created. So these roles would have a preset run list of recipes to run. So you can forget about the old node and just run those recipes on the new node, and then you're good to go. As we've scaled, we've developed a convention of assigning one vault item to a role. So essentially, we have a one-to-one mapping of vault items to roles. And this made our procedures more or less self-contained. However, we also have a case wherein we'd have nested roles. So in this case, we have 4 levels in a nest. And the depth of the nests are arbitrary. So while maintaining a one-to-one mapping convention, we would actually recursively go through the nests to flatten them out. And whenever we do vault operations, we go through this list. We remove the old nodes from that vault item and add the new nodes accordingly for each one. So typically, this would be passed in as an argument in your knife bootstrap, if you're familiar with that. Another issue that we've faced as we've scaled to multiple environments is handling of different credentials specific to that environment or logical grouping. So by default, you'd have this convention of secrets. So one vault item would be associated with one environment, which is ideal for some setups, but we're optimizing the overhead for managing multiple data centers, multiple environments, or any other logical grouping that you might have. So what we did is basically leverage one vault item for a logical grouping of credentials to use multiple environments. So this is an example that we can have. So essentially, for each vault item, you can have multiple environments, and you'd have a helper function pull these secrets. So let's say in dev, you'd want to pull this set of secrets for these specific nodes. Or you can go to stage and just have those nodes only access the secrets for that grouping. And you can also have a wildcard for, let's say, a data center that you might have, or another environment before staging, before prod. So lastly, we want to be more proactive in protecting our systems. So how do we detect secrets that aren't supposed to be where it is, and how do we actually delete them in our infrastructure? So we actually leverage machine learning to do that. So these are the features that we found useful in analyzing strings. So you can have your string length, the number of unique characters, uppercase characters, lowercase, number of digits, number of symbols, and we can also have entropy, which I'll be going through later. And we've built models to detect secrets based on these features. Our first model was using k-means clustering. So it is an unsupervised learning technique which partitions observations in k-clusters. So basically, you can have clustering based on length, number of unique characters, uppercase characters, etc. And you'd have to basically analyze them and figure out which clusters are actual secrets or not. So some of the data points that we've seen. So this is testing against 10,000 positives. And as we went through the tests, it was actually pretty scattered. It was all over the place. So for example, we have 463 data points that could be a secret or not against running against 10,000 positives. And our accuracy is actually 39%. And as we go through the different tests, there wasn't any like useful conclusion out of those. So instead of using k-means clustering, we actually use SVMs, support vector machines. So SVM is a supervised learning technique that builds a model that assigns a new data point to one category or another. So based on the features that you might have, you can train your model to detect whether or not the underlying string is a secret or not. So some data points. So we went through multiple iterations, this time testing against 1 million positives. And as we've trained the model, it became more and more accurate. And as you can see from model 1 to model 5, there's a huge difference in accuracy. But in model 6, we've seen a decline in accuracy, mainly because of overfitting in our model. And these data results could be different for everyone. So make sure to always check the numbers. So we've detected the secrets and know in the ballpark where to delete them. But how do we ensure that the secrets that we have are actually strong enough? There are many ways to do this, but we're using Shannon entropy to do that. So I don't know if you're familiar, but in information theory, you can actually correlate the strength of your secret based on entropy. That's the formula for entropy. So basically, it's the negative log for the probability mass function of that value. In simpler words, the higher the diversity of characters, the higher the entropy, which could then translate to higher strength of your secrets. The more diverse your characters, higher entropy, higher strength. So what's next? We actually plan to share our actual optimizations in our GitHub sometime in the future. So feel free to check us out in the next couple of weeks or months. Let's see. So with all that being said, a little bit of background about AppLovin. So in the intro, he said that AppLovin is as he said, AppLovin is a mobile marketing platform. So we basically help mobile game developers grow their businesses, whether that's helping them to publish, monetize, or market their games. We're based out of Palo Alto, but we also have offices in San Francisco, Dublin, Toronto, Beijing, Tokyo, Seoul, and Berlin. And we've been consistently ranked as one of the best places to work at by multiple agencies. My team specifically finds ingenious ways to solve problems, and we are actively hiring, so if you guys are interested, feel free to contact me. Yeah, that's it. Do you guys have any questions? Cool.
It's because we want them on recording.
Sure.
Hey, so I was wondering how you maintain your data bag and your data bag items for the vault. Did you maintain those like in a repo, and you had a pipeline when those needed to get refreshed and updated, or did you keep an external source other than the Chef server?
So are you talking about the Chef Vault specifically, or?
Yeah, the Chef Vault, your Chef Vault items.
So Chef Vault is built on top of encrypted data bags, and for us, our encrypted data bags are within our Chef server.
Is that the only place? That's my question. So did you maintain them externally as a definition?
No, it's in our Chef server.
Okay.
Yeah.
We run into the problem where we would need to have a lot of Chef users in order to maintain and access, like putting in new secrets.
Right.
Do you get around that? Because some of our developers, I don't want to actually give them Chef access. Do you have any novel ways you've worked around that?
We actually have specific lists of people who have access to our Chef Vault. And basically for each Vault item, there's going to be a different list of people. And that's how we're controlling access to those.
This is a little less of a question, more, I saw that you have multiple environments all sharing a same encrypted data bag. That may not necessarily be the best approach, because in a lot of cases, the development stage or the QA stage may not have the same security measures.
Yeah.
And so one trick is to shard based off of the IDs, and you just create a new set of secrets for each environment.
Cool. Oh.
Yeah, I had a follow-up question to the question about how do you maintain like fine-grained access to the vault items. So are they just file permissions
Based on the
then?
users, or based on like the nodes which has access to the vault?
No, users. So you have a pool of users who can log on to the Chef server, but you only want like a subset of that pool to access like vault item A.
Right.
How did you do that?
Yeah, so we have specified lists of people.
Yeah, so kind of like what format of those lists are? Like, are those like file permissions on the server, or?
Basically just actual lists, and we would do like a -A, specify for each user in that list, we would do a -A, that user, and that specific user would then have access to the vault item.
Okay, so no automation around it, where like you have like a list of users in a data bag that like maps to a bunch of vault that they should have access to that gets automatically processed, right? And so like if a new SRE joins your team, you're gonna have to run knife vault update -A this user for all your vaults, right? You don't have an automated script to update all your vaults for that new user.
We have like a wrapper script on top of that. Yeah.
So it's like a shell script that somebody wrote.
Yeah.
Same thing that everyone. So you don't auto prune people off those lists. It just happens.
Basically, when you remove, so you can essentially just run the refresh, right?
Yeah.
And remove the user from that vault item.
And just sort of how we approach it is because if you look at how the users are stored, it's in the underscore keys data bag. And so you can generally just do a full search of that and just script that process
Yeah.
as well.
Yeah. And another option is when you do sparse mode, each user would be represented in a separate file. And you can essentially just delete that file as well, instead of having everything in a single JSON blob. Cool. All right. Thank you, everyone. Have a great ChefCon.